Okay, so first thing, if you were away last day, the review for the unit is over on the counter underneath the Muppets. Okay, so you can go grab one of those for yourself if you don't have one yet. We also have this handout here. Where did it go? Which is about standard solutions. And I'm not quite sure why it's as long as it is. It doesn't really need to be this long. But I forgot to put it in the workbook. So here it is. This is for titrations. What is a standard? You guys should know this at this point. What is a standard? That is our known. What is known about the standard? Concentration. Okay, so it's just defined there as a solution of known concentration. Now, a primary standard, if you guys don't know the symbol for primary, it's a 1 with a little degree sign. That means primary. Handy for those of you who are in biology and need to do primary, secondary, and tertiary protein structures. Also handy if you take organic chemistry and you have primary, secondary, and tertiary amines. At any rate, this is a standard, and it is a standard solution, and it has to be made from something which is pure, something which is non-hygroscopic. Now, I don't know where this hygroscopic came from, but hygroscopic means water absorbing. Have you guys seen like brown sugar and how it's kind of gooey? Yeah? Brown sugar is hygroscopic. It absorbs water when water is present. And so if you were to weigh out some brown sugar, it would not be 100% sugar. It would be sugar and some percentage would be water. And if you were to evaporate the water off, you would end up with the pure sugar. Okay? Now, as it turns out, one of our very favorite substances for titrating with, sodium hydroxide, the solid form is very hygroscopic. So we can't actually know when we weigh out sodium hydroxide how much sodium hydroxide there really is, because if we weigh out 10 grams, maybe only 95% of that is sodium hydroxide and the rest is water. But we don't know that it's 95. It could be 97. It could be 94. We just don't know. And if you don't know the mass of the solid that you weigh out to make the solution, can you know the moles? No. And if you don't know the moles, can you know the exact molarity? No. So how on earth are we going to get some standardized NaOH when we can't just weigh it out and know how much we get? Okay. Well, what we're going to do is we're going to use a primary standard to standardize, to find the concentration of our sodium hydroxide, which we only know kind of approximately. So in order to be a primary standard, it has to be pure, it has to be non-hygroscopic, and it should be a crystalline solid. These are the properties that allow you to measure out a mass and know that the number of moles you're getting, because all you're getting is that pure solid, nothing else, no other gunk in there. Oxalic acid dihydrate is, now there is water, but I'll explain the difference between the water and the water, okay? It is pure. It is non-hygroscopic and it is a crystalline solid, so therefore it is a good primary standard. So if you weigh out 10 grams of H2C2O4.2H2O, you know that all you've got is C2H4.2H2O. In this formula, there are specifically exactly 2 waters embedded in the crystal lattice for every 1 H2C2O4. There's not a random amount. Okay, so when something is a hydrate, that doesn't mean that it absorbs water in a hygroscopic way. It doesn't mean it just randomly absorbs any old amount of water. Okay, hydrates are still considered pure because they have a specific amount of water that you know ahead of time. If we can make a solution of this acid, can we titrate NaOH with it? The answer is yes. My block 8 said I go too slowly, so I'm going to start answering my own questions and stop going as slowly as I did before. If you would like me to slow down at any point, please let me know, and I will absolutely do so. So if we make a solution of this acid, can we titrate NaOH with it? Yes. And this will standardize the NaOH. In other words, we will find the actual concentration of the NaOH. Okay, so NaOH absorbs water from the atmosphere. Tell your partner, what is that word that means absorbs water from the atmosphere? Tell your partner, what is that word? High? Not hydro, but high-grow. You can think maybe it grows the mass of the substance because it adds water in there. Hygroscopic. So if you measure out 10 grams of NaOH, you're not really getting 10 grams of NaOH. You might have X grams of water in there, and we don't know how much that is. But what I do know is that you have 10 minus X grams of NaOH. And so if you were to take these 10 grams and you could maybe use that to prepare a 0.1 molar solution of NaOH, but it would only be approximately because we don't know for sure. So what we do is we prepare a primary standard, say 0.5 molar H2C2O4, 100 milliliters of that, and use it to titrate the NaOH. This allows us to find the concentration of NaOH precisely. This process is called standardization because we are finding the concentration. The concentration will be known. At that point, the NaOH is said to have been standardized. What I would like you to do right now, and you might need some extra paper to do this on, I don't know if there's enough room there for you at the bottom, do the calculations to figure out, and this is because you're going to be doing this in a lab next week. Okay, so I need you to figure out how to make a 0.05 molar, 100 milliliters of 0.05 molar H2C2O4, starting with solid oxalic acid dihydrate. Off you go. When in doubt, find the moles. When in doubt, find the moles. Start with that. Yep, you'll want your pink book because you need some molar masses. Anybody need a data booklet? Okay, when in doubt, find moles. Okay, so you have 100 milliliters of oxalic acid dihydrate. If you need extra paper, does anybody want paper? No, already. Yeah. What is oxalic acid dihydrate? Yeah, it is H2C2O4 dot 2 di H2O. Okay, so when you are finding the molar mass, you must include that water in the molar mass.
Why is it dot again?
Because it means is attached with, is embedded within the crystal. That's just how we write the formula of a hydrate. Okay, yeah. Did you guys get 0.63? Excellent. What would you do with that to make 100 milliliters of solution, starting with the solid? So you've got this solid. And presumably you've measured it out in maybe a beaker. What are you going to do with it? Add water into the beaker?
Where?
Okay, if we add water into the beaker, how much water would we like to add into the beaker?
You're gonna say
100 milliliters. So if I add 100 milliliters to that solid, will I get 100 milliliters of solution?
no.
No, because the volume of the solid takes up space. So I cannot just add 100 milliliters. How do I end up with 100 milliliters of solution?
Add less water.
Add less water. How much less water? How would I know that I end up with 100?
No.
I don't. So that's not a good solution, is it? Haha, that's kind of a pun also. Not a good solution for not a good solution. Okay.
What do we have to use rice?
No, you don't need to use rice. Oh my God, no. We're just making a solution. Does anybody know in which kind of container we should actually be making this? We should not be making it in a beaker. Why not in a beaker?
Even not in the flask. Even not in the flask.
What in what kind of a flask?
Or the wine.
An Erlenmeyer flask.
Why?
I don't know why either. I'm asking, why in an Erlenmeyer flask? What's better about an Erlenmeyer flask?
Maybe we can titrate it with some.
We can titrate it with something. The whole point is that this one, we do not need to titrate it. We can just make it and boom, it will have the exact concentration we want because that many grams will give us exactly the right number of moles. Yes. It is easier to mix. So we've made progress in the right direction. Okay, we're not quite there yet though, because I still want to know how I'm going to end up with 100 milliliters of solution. Because in order for this to be precise, I not only need precise grams, I also need precise volume, milliliters. I need to be at exactly 100 milliliters. Can I get to exactly 100 milliliters in an Erlenmeyer flask? If this is the 100 milliliter mark here, can I measure that to exactly 100? No, why not? Because Erlenmeyer flasks are big and wide. What is the problem with them being big and wide? It won't be as accurate. So can we think of something that would be less big and less wide? The tube. What kind of tube? I don't know what it's called. Okay. Yes. You could use a graduated cylinder, and that's not a bad choice. Okay. I can't draw a graduated cylinder, but anyway, that's kind of what it looks like. A little bit. That's a pouring thing. Pouring thing. Grad cylinder. You could do that. You could put in the 0.63 grams, and then you could fill to 100 milliliters. Yes? Better, because a 100 ml grad cylinder is this thick. It's this wide. Does that look really skinny to you? Still fairly wide. Nobody knows? If you were in my class last year, we made solutions in this container. You ever seen one of these before? Oh. What is that? The one that this is a volumetric flask because it's only got one volume on it. And that volume is 100 milliliters. You see how skinny that is? Yeah. One drop of liquid is going to make a big difference, right? So you can be very, very precise in your measurement. Whenever you're making a solution and you want to be precise, you want the skinniest neck possible, okay? So we don't want any of those. We definitely don't want a beaker because wide, inaccurate. We don't want an Erlenmeyer flask, wide, inaccurate. Graduated cylinder, if you don't have a volumetric flask, it is a better choice. But if you have a volumetric flask, that is the best choice. Okay? No, it is exactly 100 milliliters when you get to that line. Okay? So what you're going to do is you're going to put in your solid. And then you're going to add water, but you're not going to add it all the way. You're only going to add it halfway. Anyone want to guess why? If I add water all the way to the line, and if I had solid in there, which I don't right now, but if I had solid in there and I needed to stir it to make it dissolve, how easy is it to stir? Not very, but if I only fill it halfway, how easy is it to stir? Very easy. So what we're going to do is we're only going to fill it halfway so that it's very easy to stir. And then once it's all dissolved, then we can add water to the line. Once you've dissolved it, you've added water to the line, then you're going to put a stopper on it. You will not use your thumb. I will use my thumb right now because this is just water. Okay, and then you will invert to mix. All right, and let's just take a look here. There's our calculations. Here is how we would describe it. You would weigh out, this is on your next page, 0.63 grams of H2C2O4.2H2O, probably in a beaker. In a beaker. How would we get the solid into the, what's this called? Volumetric flask, because that's a skinny, narrow little neck, yeah? How would we get the solid in there? What might we use? A funnel. We have two choices of funnel. Which choice would be better for delivering a solid? The one that is wider, because this one, solids tend to get stuck in that tiny little opening. Yes? Now, just so you're aware for next week, these, sadly, don't fit. Okay, but we still want to use it. So what we're going to do is we are going to just hold it right on the top. Does that make sense? Okay, and if we had a bigger budget, we would get better powder funnels. Okay, but we don't, so there we are. So we transfer the solid in. Ooh, I have my little beaker. It had solid in it. If I transfer it all, do you imagine that all the solid's going to come out of the beaker, or do you imagine there might be a little bit left behind? There might be a little bit left behind. So you are going to use a wash bottle. You use a wash bottle to rinse out the beaker. Yes, rinse out anything that's in there, and then transfer it into the thing here. Okay? Now, when you are filling it, fill. The line's right there. Now, let's say I am filling it with a beaker. You see where my finger is? Let's see if I can put my finger there. There's my finger. That's where the line is. Oops. Where's the water? Here's the water, here's the line. What do I need to do now? I added too much water. Do I just pour the water out? No, what do I have to do? I have to start over. I cannot, like, too bad, so sad. My solution is now ruined because I don't know what the concentration is anymore. I have some random volume. So instead of willy-nilly just filling it with the beaker, you might, when you start to get close, start to fill it with the wash bottle. And then when you get really close, did I not just grab one? What did I do with it? I grabbed a medicine dropper, but I cannot see it. Oh, there it is. When you get really close, you can start using a medicine dropper. Yes, and that'll make sure that you don't go past. And it takes a little bit longer, but not as long as remaking the whole thing from scratch. Yes? You're going to swirl to dissolve the solid. And then you will add water to the calibration line using an eyedropper for the last bit. And then you will stopper it. We have stoppers. If you want to use parafilm instead, it's really awesome. Let me know and I can help you with that. It is pretty cool stuff. And then you will invert it to mix. If you are asked to describe this process, please do not say, I will flip it to mix it, because flipping is like this. This is flipping. And I am not doing that with my volumetric flask. I'm going to, if you don't like the word invert, because you're like, I don't really know what that means, just say turn it upside down to mix. Okay, turn it upside down. All right, and that is, voila, we have a primary solution, and we can then titrate our thing. And then this is just a little picture of what is happening here. La, 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 la. I don't know why I have that page, but it made an even number of pages. There is a description here of the primary standard, a description of non-hygroscopic, and the procedure has a lovely little picture down at the bottom. Yes? You should know that procedure. That is what you're going to be doing in your lab on Monday. Okay? In your lab on Monday, you're going to be making that solution. Okay. Over the weekend, yeah. Okay. All right. Why did I close that? That was not what I was supposed to do. So that is a standard solution. Let's finish up the rest of titrations. So we are on 5.6b, and we made it to, where did we make it to? We made it to here. Okay. So we are On page 97. You awake, Owen? Not you, Owen, you, Owen. Okay. Okay. Titration of a weak acid with a strong base. If you remember, look at this graph and tell your partner what tells you that this is not a strong acid, strong base, but rather a weak acid, strong base. Describe to your partner how you know that that is a weak acid, strong base, not a strong acid, strong base.
And that's pretty much it.
You should recognize that at the very beginning, what do we have? We have a little hill. You should recognize that the equivalence point is greater than pH 7. And you should recognize that the vertical section is shorter. Does it take any more or less base to get to the equivalence point? Does a weak acid, 0.1 molar, require more or less 0.1 molar NaOH to reach the equivalence point? Compared to 0.1 molar HCl. Remember, the equivalence point is when the moles equal the moles. Yes? Let's say I give you 3 moles of HA. HA. That's representing 3 moles of HA. Yes? Ha ha ha. No, nobody's going to laugh at that? All right, fine. And let's say we had 3 moles of HCl. HCl. Huckle. Thank you for laughing. I appreciate that. Okay, anyway, we got 1, 2, 3. And we got 1, 2, 3. Which one will require more NaOH to neutralize it? So in HCl, I need to neutralize 1 H, 2 H's, 3 H's. In the weak acid, I need to neutralize 1 H, 2 H, 3 H's. Does it require any more or less? No. The only thing about that's different is that in HCl, the H is already off in solution, whereas in the HA, the NaOH actually needs to rip it off of the acid. Okay? But the equivalence point will be the same if we have the same concentration and volume of acid. We good with that? Does it require more or less? No, requires the same amount. If moles of acid are the same, the strength doesn't matter. Both will require the same moles of base. This is a question that students very often get wrong because they think it's going to take more base to neutralize the strong acid. And it doesn't, okay? Because the moles of hydrogen are the same in both. All right. Why is the pH at the equivalence point greater than 7? We got a weak acid and a strong base. Why is the equivalence point pH greater than 7? That's the answer I always get. That's the answer I don't want. Thank you for providing it. Okay, you are not the only one. That's the answer I get from all the students all the time. Because it's a weak acid and a strong base, therefore it must be basic. No. What do you have at the equivalence point? You took your CH3COOH, your weak acid, and you took your strong base, and you reacted them all. They're all gone, all reacted. You have no strong base left. You have no weak acid left. This is at the equivalence point. Right? We've reacted them all. No excess of either. What do we have? When we react an acid with a base, what do we get? We get a salt plus water. And when you see a salt, what should you think? You should say hydrolysis. Na plus? No. CH3COO minus? Yes. That's going to give you OH minus, therefore it's going to be basic. So when you are asked, why is the pH greater than 7? It's because the weak acid has all been turned into its conjugate base, and that conjugate base hydrolyzes, and when that base hydrolyzes, it gives you hydroxide. Okay? So why? Into it's going to be part of the salt. The weak base hydrolyzes, producing hydroxide. Is good. And yet I'm still going to get people telling me that it's because there's a strong, the base was strong, the acid was weak, therefore it's basic. That is not the answer. Okay? At the equivalence, you should be looking for hydrolysis. What should you be looking for at the equivalence point? Hydrolysis. What should you be looking for at the equivalence point? Hydrolysis. Okay? And then after the equivalence point, what have we added? We've added more base. And I don't know if you remember, but back when we were in mixtures of strong acids and weak bases, after the equivalence point, we did a bunch of calculations, which you don't really need to do. But after the equivalence point, this was on page 71, if you want to look. After we have neutralized all of the weak acids, so for example here, we had 4 millimoles of the weak acid and we had 6 millimoles of the strong base. That means we have excess strong base, yes? So when we do the calculation with that, our final concentration of the weak acid is nothing, and we end up with some strong base. Yes, this is page 71. Now, if we calculate what is the concentration of the strong base of the OH, it's 0.2 molar. What else is in our flask? Well, we neutralized all of the CH3COOH. We ripped off the hydrogens, and now all we have left is CH3COO minus. We have that conjugate base left, and we have 4 millimoles of that weak base. Will that weak base make extra OH minus even on top of this amount here? Yes. Will it make enough to make a difference? No. And we did the math down here, and we found that the extra OH minus was 1.11 times 10 to the negative 9 molar. Is that enough to make any sort of a difference? No, because we're dealing with, like, that's compared to 0.2 molar. Yeah, and compared to 0.2 molar, 0.00000. 1. Too small. Yes? So after the equivalence point, we only care about the extra base that has been added. So going back here, after the equivalence point, only the excess base matters. So this is now on page 98. If you're asked to calculate this, you would use a RICFA table. To calculate moles of OH minus in excess. Then the concentration of OH minus. So you should, the takeaway message from this is that you should be able to look at those two graphs, the weak strong and the strong strong, and be able to tell the difference between each other. Yes? Okay. Here's a graph. We have 50 milliliters of 0.1 molar acetic acid. We are on page 99. Page 99. 15 milliliters of 0.1 molar acetic acid, and it's titrated with 0.1 molar NaOH. If we swap 50 milliliters of 0.1 molar HCl for the 0.1 molar acetic acid, would the amount of base needed to reach the equivalence point change?
No.
I hear a no. Why not?
I mean, the same thing.
It's exactly the same thing. You have the same moles. So, no. That's not supposed to be an R. That's supposed to be an N. No. Same moles of acid requires same moles of base. That's supposed to say requires. I don't know what's going on with that. I'm just reiterating the same point again. Would the pH at the equivalence point change? Would the pH at the equivalence point change if we replaced the acetic acid with HCl? Yes. What would it become? Yeah. Because the salt is, what's the salt if we have NaOH and HCl? NaCl. And when you see a salt, what should you ask yourself? Hydrolysis, is there any? No.
So pH would.
Hmm?
So pH would.
Yes, yes. pH changes, it would become pH equals 7 because the salt is NaCl and there's no hydrolysis. So the volume taken to get there would be the same, but the pH at the equivalence point would be different. Okay, excellent. There's pictures down at the bottom. Feel free to look at them if you want to. We're going to keep going because we need to be done this. Ooh, look at this. How can we find the pH? How can we find the Ka of a weak acid from its titration curve? How can we find the Ka? No. In fact, let's go back to the previous one so we're not looking at too many different ones. Let's find the Ka. Let's go back to page 99 and let's look at this. Find the Ka of CH3COOH from this graph?
But
There's actually a couple ways to do it, but there is one really easy way to do it off this graph.
oh, we look at the negative 8 something to negative 12. Does that make sense?
We don't want to go to the equivalence point. We want to go to the half equivalence point. What is true at the half equivalence point?
Constant Ka is equal to concentration of
Ka is equal to concentration of H plus. At what volume would we have our half equivalence point here? 50 mils is our equivalence point. Where's our half equivalence point? 25. And we go up there and we say, okay, there's our half equivalence point. There we go. That is approximately, what would you guys say? 4.9-ish? Okay. And that would be the pH at the half equivalence. Therefore, H plus would be 4.9. 1.3 times 10 to the negative 5 molar, and so Ka would be 1.3 times 10 to the negative 5. And what do I have in my data booklet? Let's see how close we get. I think it's 1.8 times 10 to the negative 5, which is not bad for just reading off a graph, right? And if you actually had a pH meter, you would be able to get that more precisely, right? So that's not bad. You could do it another way as well. You could find the concentration given the whole thing, you know, the titration, and then you could use the initial pH, right? And you could be like, okay, my pH is this and my concentration was that, and then I could find the Ka, but that would take a lot more work. And pretend I didn't say anything because I probably just confused you there. All right. How does the pH at the equivalence point change as the acid becomes weaker? So these are a bunch of different acids, each with different Ka values. We have 10 to the negative 2, 10 to the negative 4, 10 to the negative 6, 10 to the negative 8. Those are our Ka values. Which of those is the weakest of those weak acids? What color line gives us the weakest of those weak acids? The dark blue line. This is our weakest. And what can we say about its pH at the equivalence point? The pH at the equivalence point is highest. That kind of makes sense, yes? We start at pH 7 for a strong acid, and it just gets progressively higher and higher and higher as the acid becomes weaker and weaker and weaker. How does the volume of NaOH needed to reach the equivalence point change? Everybody. What happens to the volume of NaOH needed to reach the equivalence point as the acid becomes weaker and weaker and weaker? It always requires the same amount. Okay, excellent. Good, good, good. And now we're going to do a weak base with a strong acid. Okay, there's our weak base with a strong acid. You'll notice, what do we have at the beginning? Weak base, strong acid. We're now on page 101. What do we have at the beginning? We have a little hill. Yes, a little curve. We have a half equivalence point. All right, as well, we have an equivalence point. The half equivalence point is still going to give you Ka of the acid because it's a pH. What would a strong base, strong acid look like? So if we were to then do a strong base plus strong acid, what would that look like? Would it start at the same point, or would it start higher, or would it start lower? Strong base would start higher or lower than a weak base?
Higher.
Higher. Okay, so this would be our strong base. Ooh, why is the equivalence point here is less than 7? Why? At the equivalence point, you should be thinking, I have no acid, I have no base, I only have the salt plus water. And when you see a salt, you should be thinking hydrolysis. And if this was NH3 plus HCl, that's our weak base, plus our strong acid, what are our products there? NH3 plus HCl.
Oh wait, NH4.
NH4 plus Cl minus. There actually isn't any water involved in this, okay? We just get the NH4Cl. Do we get hydrolysis? Yes? No. Yeah? NH4 plus reacts with water. What do we get? NH3 plus H3O plus. So the hydrolysis of the weak acid results in H3O plus, therefore it is acidic. Is good? Okay. All right. There's a bunch of questions. We're not going to do them right now. We're going to go on to choosing an indicator. Okay, choosing an indicator for an acid-base titration. Oftentimes in an acid-base titration, an indicator is used rather than a pH meter. Optimally, the indicator should change color at the pH of the equivalence point. But if you look at a strong acid, strong base titration, what do you notice about the pH at the equivalence point? The equivalence point takes place at 25 milliliters, and really there is no change in volume. Of NaOH added from pH 3.5 3 to pH 10. Right? I go from pH 3 to pH 10. Did I add any more NaOH in there? What's the change in volume from here to here? How much volume took us to pH 3? No, how much volume took us to pH 3? 25 milliliters, yes? How much took us to pH 7? What volume took us to pH 7? 25 milliliters. What volume took us to pH 10? 25 milliliters. So if I am looking to find my equivalence point is at 25 milliliters. Does it matter if I choose an indicator that changes color at pH 7, the actual equivalence point, or could I choose anything that changes color within that vertical range? Will that also give me the volume of the equivalence point? If I chose the indicator methyl orange, which changes color, pH 3.2 to 4.4, what volume will it change color at? 25 milliliters. If I choose the indicator phenolphthalein, at what volume will it change color? 25 milliliters. If I'm looking to identify 25 milliliters so I can calculate the moles of base, does it matter if I choose something that changes color after pH 7? Because I get the same volume either way, okay? So you actually have a lot more choice than you think. You might think, this is a strong acid, strong base. Where did my nice pen go? I don't know. That's okay. If I have a strong acid, strong base, my pH at the equivalence point is 7, so probably we would want to use bromthymol blue. That's very nice, except for bromthymol blue changes from blue to yellow or yellow to blue. I cannot remember which way. And that would mean you would need to know the exact shade of green where the equivalence point is, yes? Phenolphthalein, on the other hand, changes from from colorless to pink. So all you need to know is that the moment you get the very first hint of pink, you have reached the equivalence point. So we choose phenolphthalein, even though it changes color at a pH after the equivalence point, because it doesn't change at a volume after the equivalence point. It changes at the same volume, and it's a really easy to see transition point. Okay? What does matter, though, is that you cannot choose something like methyl violet. Okay? Bromphenol blue would be fine, just like methyl orange would be fine because they change color within that vertical region. Methyl violet, however, changes pH 0.0 to 1.6. If we used methyl violet as the indicator, would it change color at the equivalence point? No. If we were to choose alizarin yellow, it changes at pH 11.4 to 13. Would that be a good choice? It's a dodgy choice. It's almost within that region. You're like, maybe, but it's getting a little weird. Yes, phenolphthalein is nicely within the range. Okay. So you need to be able to look at a titration curve and say, phenolphthalein is a good indicator for a weak acid, strong base titration Because the pH at the equivalence point is greater than 7. And guess what? Phenolphthalein changes at a pH greater than 7. Do you remember how methyl orange was okay for that strong acid, strong base? Because it changed at the 25 milliliters. How about methyl red, which is similar to methyl orange? Would that be good for a weak acid, strong base? What volume would we hit at the equivalence point, or at the end point, sorry? What's an end point, by the way? The end point is when the indicator changes color. Take a look at that graph and figure out at what volume does the indicator change color. $4.8 to 6, but specifically at what volume? Right in the middle of that. So that would be at about 30, I don't know, 33, 32 milliliters. Yeah? Does that make sense? Okay. 32 milliliters. So the volume of NaOH needed to reach the endpoint is 32 milliliters. The volume needed to reach the equivalence point is 50 milliliters. Is methyl red an appropriate indicator for that strong base weak acid titration? No, because they don't match up. You need the endpoint and the equivalence point to be like they need to be the same volume. When we look at the phenolphthalein, what's the volume of NaOH to reach the equivalence point? That's still 50. What is the volume of NaOH needed to reach the endpoint where the indicator changes color? Also 50. Is that a good choice? Yes. So you need to be able to read graphs like this and say, oh, is that a good choice or is it not a good choice? There are some exercises here. Okay, so you would be doing exercises from 5.6b and 5.6c. Okie dokie. And does anybody need a copy of the overall review? Anybody? We all have it? Joshua, you got a copy of the review? You got it? Cool. Excellent. And I think we'll be leaving out section 5.7 because we don't have time. Okay, so there we go. 5.6D, you've already done some of the calculations in there over the weekend. If you did the homework, were they okay? If not, add in a few more of those as time goes on, okay? They are exactly like what we did in terms of titrations for the solubility unit, except for now it's acids and bases, and there might be a 2-to-1 ratio, okay? Use stoichiometry for titrations. And I'm probably preaching to the crowd here because you guys are the guys who are here. Yes?
Yeah.
You are the ones who are here. But if you're not here for the test on Friday, you get a special test next week. You do not want to write the special test next week. You want to write the test that is happening on Friday. Do we understand each other?
Yeah.
Okay.
Really don't want to write this test next week.
You really don't want to write the test next week.